Hello, this is the third question of assignment 3 in data analytics course. In this question, we mainly focusing on principal component analysis, where we use this principal component analysis, which is also known as PCA, to dimensionally reduction. Here, this PCA acts as a feature extraction method. Let's dive into the code. So here in the first part, we have implementation of correlation matrix and covariation matrix. These concepts are here to give the basic mathematical concept in this PCA. So let's go to this. Here in the first part, we are importing pandas and numpy and creating a matrix, a simple matrix, and printing it. Here we using the np.con function to convert this matrix to a covariance matrix. Then again, we try to, in this tutorial, try to convert the correlation matrix using a matrix. So for that, they are initializing a matrix. And then they convert that matrix to a correlation matrix using the inbuilt function co. As you can see here, this is the same matrix as above. If we understand it further, this matrix, what's more important of this is that this shows the correlation of each features. If we see this one indicate that the correlation between the zeroth feature and the zeroth feature. That means itself. So since itself has a higher correlation 1, it shows correlation 1. If we further analyze this matrix, correlation matrix, we can see that we have negative correlation and positive correlation, and so the highest correlation, highest negative correlations we can see is that between here we can see that between one feature and the third feature we had some negative correlation, and like so in here we have another high negative correlation. If we consider the third feature and the second feature, we have a positive correlation. So now we have a basic understanding of what's correlation matrix and how to obtain it, and what's covariation matrix is. So let's dive into the principal component analysis on the iris dataset. So here in this tutorial, we have imported the basic components needed to this tutorial, and they are loaded in the iris dataset, and they are getting those data using the data frame to the df variable and printing it. Here we can see that there are 150 instances along with 5 columns. So since this every column is not needed, they are separating it to X the needed features and Y the class labels. Then they are printing the shapes. As you can see, there are 150 instances and 4 features. As we know about iris dataset, this is petal width, petal length, sepal width, length, and sepal width. So this is the implementation of PCA. Let's come to this later, since it will be called upon in down the line. This is standardization, where we rescale our x values to a Gaussian distribution with zero mean and unit variance. This is a very important step when it comes to PC. So we are doing this to scale our data to a standard manner. If we consider the data set, if we doesn't scale it, there will be variance in the data set, and we couldn't get much accuracies when doing the analysis. So standardizing the data when it comes to the principal component analysis is much more important. So in this step, we are initializing the function in above steps, that is converse PCA. Here it initializes with two components. That means here we try to reduce the features to 2. Let's dive to the algorithm. Since here it passes 2, it will come here. It will initialize the converse PCA function class. So as you can see, number of components will become 2, and eigenvalues, eigenvectors, variables will be also initialized. Then what happens is that it uses the initialize object and use the bit function to function and pass the transform data to the object. So let's go again to the bit function. As we can see, it take a variable, the standard data set, standardized data set. In here, in the first line, we can see that it takes the number of components. If the number of components is not initialized, it will take the shape, that means the original number of features. Then what it do is calculate the mean using the NP numpy. Then it calculates the covariance matrix. As I explained in the previous step, this covariance matrix and correlation matrix both are used to find the eigenvalues and eigenvectors. This covariation matrix and correlation matrix both can be useful to do this task, because since covariation matrix, normalization gives the correlation matrix. As you can see, we use the np.co and pass it our standardized dataset and reducing the cell mean, the mean we calculated earlier. And we pass the provar variable as false. Then it calculates the covariance matrix. In the next phase, what we are doing is assign eigenvalues and eigenvectors using covariance matrix. We use the link functions to obtain these values. Then we transform the eigenvectors and assign it to the eigenvectors. Then what we do in this algorithm is that sort in these eigenvalues. We sort these eigenvalues to obtain and find out what are the highly variance features, highly variance principal components. These highly variance principal components will have the less correlation. So to do that, we are sorting these features according to eigenvalues. Then what we are doing is taking the projection matrix. We are doing that by taking and finding out the minimum components from the sorted components, as I explained before. So we are calculating the projection matrix by taking the eigenvectors with minimum correlation. In here, what we are doing is we are calculating the explained variance. Even though in this tutorial we don't use this explained variance or the explained variance ratio, this will be useful to plot scree plot, where we can see the explained variance ratio against the principal components. So these values will be useful to get a visualized idea. If I explain this further, here to get the explained variance, we use the eigenvalues and the sorted components, and to get the explained variance ratio, we divide the explained variance by eigens values sum of the eigenvalues. I have explained it here. So here I also explained that we can use this plot to see the variance and ratio in the scree plot. So since now we have understanding on the algorithm, let's dive into the plotting. To plot the dataset, we use the transform function in this object, PCA object. If we go back to this transform function, what it do is it use the projection matrix which calculated earlier to reduce the dataset, reduce the dimensionality of the dataset. In particular, in this step, we use the projection matrix to reduce the number of dimensions to 2. Since in the initial step we had 4, now we will have 2 features. So we use that the outcome from it, the return value from here to std variable. Then we use the xstd variable to plot the scatter plot. As we can see here, since we have idea on the iris dataset, the 3 classes we see on the typical dataset is plotted using the reduced dimensions, 2 dimensions, which has the highest variation and the meaning least correlation. So I use that knowledge in the later part to apply this algorithm to breast cancer dataset. Before that, here I had included the answers for the questions. What PCA is, I have explained in this tutorial also. So if I go to these answers a little bit, so this PCA, also known as principal component analysis, used for dimensionality reduction. So this will transform a larger set of variables into a smaller one that will consist the information which consists in the large set. So I have explained it here briefly. So here I also explain that how we can use PCA for dimensional reduction and visualize the classes. If I go to it also, here I explain the procedure we go to in the earlier steps, like calculating the covariance matrix, routing the training data, and finding the eigenvectors and eigenvalues from the covariance matrix, then sorting these eigenpairs and getting the eigenvalues which consists of the highest variance, then constructing the projection matrix for the selected eigenvectors and use that projection matrix to transform data into a low dimensional subspace, as we see in above steps. So we can use this to visualize data as we see in the iris dataset. So I explain that in here. So in this data part, what we answered is that why we need this normalization of data for feeding into algorithm. So normalization is a crucial task in this kind of algorithm. So we use this normalization to change the values of dataset to a common scale. So we can see this in like algorithms in k-means sphere, where we use normalizations to reduce the data to a standard scale, because this kind of algorithm use gradient distance and not scaling the data will do harm to the accuracy. And this normalization is also useful in neural network. I have mentioned it here because when it comes to the gradient, so gradient will take a longer time to approach local minima, global minima without normalization. So doing this will converge more quickly in these models. So I have explained this here. So if we go to our back to the question, in the next part, I use the previous knowledge to do this PCA in the breast cancer dataset. As mentioned in the question, I had used the previous data from the question 1. Here I am importing the drive from Google Colab, OS and the pandas, and mounting my drive, as you see, because after doing that pre-processing that mentioned in the question 1, like removing the question marks and renaming it and uploading into the drive, and I am using the data file.csv and reading it and assigning it to the data variable. Here I am printing the +q values of that data frame. These steps I also did in the question 1. So in the next, what I'm doing is dropping the unnecessary first column, then replacing the values as I did in the first question. Actually, so this is not necessary in this step, what I'm doing. Then I am coming up with the x and y and assigning the needed features. Like here, I needed here to 9 as 9 features I needed. So I am assigning it to the x variable, and I needed the class labels, and I am assigning to the y variable. Here I am printing the shape, x shape and y shape. As you can see, there are 699 instance with along with 9 features. In this question, what I'm trying to do is reduce this 9 features to 2 features using this principal component analysis and visualize it, whether it works or not. Here I am using con function to this and passing this data and printing the covariance matrix. I mean visualizing it here. Then what I'm doing is standardization of data. Since we saw it earlier, this standard scalar is much effect and much crucial task in this principal component analysis. I explained the importance of this in the previous steps. Then I am using the converse PCA function class, which I explained earlier, and passing the number of components I needed to reduce this dimension 9 dimensions to 2 dimensions. So I am passing 2. Then I am fitting the transform data. Then what I'm doing is using the PCA transform function and getting the std and use that to plot the data. As we can see here, according to the algorithm, it selected the highest variance principal components, meaning the ones which have the less correlation, and visualize it. You can see that the non-cancer patients, the malignant one in the yellow color, and the malignant, the cancer patients in this color, the purple one. So if we go to the conclusion of this question, and after doing this principal component analysis to the breast cancer data set, the main observation I took was that this PCA reductions are highly sensitive to the data scaling. I explained this in the multiple times while doing this video. And we need to standardize the features prior to PCA. Since if the features were measured on a different scale, and we want to assign equal importance to all features, because we are extracting features according to their variations, we need all these features in a similar scale. That I mentioned as a conclusion. And another conclusion we identified is that we can identify cancer patient and non-cancer patient using this plot, using these two features. So even though there are some overlap in here, this principal component analysis is useful to visualize our data and get an idea on how the data varies. So this algorithm is much effective and useful to our analyzing when doing pre-processing and doing feature reduction, and also when visualizing it. So that's my conclusion, and that's pretty much it for the question 3 explanation. Thank you.